Hello everyone and welcome to another great video about learning Azure Machine Learning. As you already know, we are talking about statistics in the past few videos, and probably this is going to be one of the last for descriptive statistics at least. In the upcoming videos, we are going to start using Python with what we learned in the theory section, let's say. So let's talk about covariance matrix and correlation matrices. So covariance, as you already know, and correlations can be calculated for bivariate data, that is data with two variables. But this can be extended to multivariate data as well. So if you have multiple variables in your data set, let's say x1 all the way through xn, a covariance matrix summarizes the covariance of all columns in a data matrix. The columns are the variables and the individual cells or elements in a covariance matrix represents the covariance between pairs of fields. There are key variables here, xn through xk. There are k rows and k columns in this matrix, and every element of the covariance matrix contains the covariance of a pair of vectors. The first row of a covariance matrix corresponds to the variable x1. This contains the covariance of the first column x1 with each of the other columns included in itself. This is true for all of the other rows as well. The last row contains the covariance of the last column xk, that is the last variable, with each of the other variables including itself. When you see a covariance matrix describing the pairwise correlation that exists between each pair of variables, you will see that the matrix is symmetric in nature, right? Like you see here. The value at row I and column j is the same as that at row j and column I. Along the diagonal of the covariance matrix is basically the covariance of every variable with itself, which is, as we know, is just the variance of the corresponding columns. So, a better way to represent this covariance matrix is that along the main diagonal we have the variance of each individual variables x1 through xk. When we speak of covariance, we had also discussed the correlation between pairs of variables. Let's move on to understanding correlation. We know that it's similar to covariance. It measures whether greater values of one variable corresponds to greater values of another. But this is a normalized representation of covariance. Its scale to be between +1 and -1. Consider two variables represented in a two-dimensional plane that are positively correlated, E and D along the y and x axis. Here is how a distribution of their data points might look. The correlation coefficient between two variables tries to capture linear relationship that exists between those two variables. Two variables are perfectly positively correlated if they have a correlation of +1. That means if as x increase, y increase linearly. Two variables are said to be perfectly negatively correlated if we have a correlation of -1. That is, if x increase, y decrease linearly. And finally, if two variables are completely independent of each other, then the movement of one variable does not affect the other. Then we have a correlation of 0. It's possible that there is an edge case that the variable may not necessarily be independent. We've spoken of the correlation as a normalized representation and the covariance, and here is the mathematical formula for it. In the real world, you may never use this mathematical formula directly, but it's important you understand how they are linked. And finally, one last detail to remember about covariance and correlation. Independent variables have zero covariance and zero correlation. And with this, we come to the very end of the descriptive analytics section. I hope you find this video informative and see you in the next one. Cheers.